Hey there, everybody. Welcome back to the Deep Dive. Today, we're going to be diving into something that sounds pretty futuristic. AI that can understand and generate speech.
Yeah, it's like something right out of science fiction, but it's actually becoming reality thanks to research like what we're diving into today.
Okay, so what is it exactly that we're looking at today?
This paper is called Llasa, Scaling Train Time and Inference Time Compute for Llama-Based Speech Synthesis. A bit of a mouthful, but basically it's all about pushing the limits of text-to-speech, or TTS.
TTS. Okay, I think most people have at least heard of that, like those robotic voices you sometimes hear on, like, phone systems or whatever.
Right, but what this research is doing is taking TTS to a whole new level. It's using those incredibly powerful large language models, the LLMs that everyone's talking about, to create speech that's way more natural and expressive.
Okay, I am intrigued. But I have to admit, I don't really get how you teach an LLM, which is all about text, to do something as complex as generate human speech. I mean, speech is more than just words on a page, right?
Absolutely. It's the pauses, the inflections, the tiny changes in tone that make a voice unique and convey all those subtle meanings and emotions. It's a huge challenge to capture all of that in a way that an AI can understand and work with.
Yeah, that makes sense. It's like you're almost translating from one language to another, but instead of like English to French, it's going from sound waves to something that an LLM can actually process.
Exactly. And that's where this idea of a speech tokenizer comes in. Think of it as a specialized decoder ring, taking those raw audio waves and turning them into a sequence of tokens.
Tokens, like what? Digital building blocks?
That's a good way to put it. These tokens represent different aspects of speech, and the LLM uses them to learn the patterns and relationships that make up human language.
Okay, I kind of get it. But how do you make sure those tokens capture all those tiny nuances that make a voice sound human? Those like little breaths and subtle variations in tone.
That's the really clever part. This paper introduces a new tokenizer called Xcodec 2, and it's designed to preserve those fine-grained details really well. One way they measure this is with a U2MOS score, basically. How natural does the reconstructed audio sound compared to the original recording?
So a higher score means it sounds closer to a real human voice.
Exactly. And Xcodec 2 is getting really high scores. It means it's not just capturing the words, but also the emotional tone, even the unique characteristics of a speaker's voice.
Wow. So are we talking about a future where things like audiobooks and virtual assistants sound just like real people?
We're getting closer. There's still work to be done, especially when it comes to recreating those really fine-grained acoustic details, particularly at low byte rates, kind of like when you compress audio.
Right, there's a balance, right? You want the audio to sound realistic, but you don't want it to take up gigabytes of storage.
Exactly. But for now, let's get back to Llasa itself. So we talked about the tokenizer, but how did they actually train this model to generate speech? I mean, where do you even begin with something like that?
Yeah, how do you teach an LLM to talk?
Well, they took a page from what's been so successful with text-based LLMs, scaling. Basically, they wanted to see what would happen if you made Llasa bigger or if you fed it more data during the training process.
Makes sense. Bigger model, more data usually means better results, right?
That's the idea. So they tested two main approaches. First, they kept the training data the same but experimented with different sizes of the model. They tried versions with 1 billion parameters, 3 billion, even 8 billion.
Whoa, those are some serious numbers. What about the second approach?
For that one, they kept the model size the same but changed the amount of data they used to train it. They started with 80,000 hours of speech and went all the way up to 250,000.
250,000 hours. Well, that's a lot of talking. So, I gotta ask, did all this scaling actually lead to better speech generation? Like, what happened when they tested these supersized model?
That's where things get really interesting. Let's dive into the results.
All right, I am ready. Let's see what happens when you try to teach an LLM to talk. All right, so we've got these massive models trained on mountains of data. What did the researchers find when they actually put Llasa to the test?
It turns out that scaling up both the model size and the data made a huge difference in how well Llasa performed.
Okay, that's what I was hoping to hear. But what kind of improvements are we talking about? Like, did the generated speech just sound more natural? Or were there deeper changes in how Llasa understood and processed language?
Well, it was both, actually. One of the things that really stood out was that the larger models got much better at understanding the actual meaning of the text they were given. A lot of the older TTF systems really struggled with that. They could say the words correctly, but it's like they didn't really get the nuances, the emotion, the intent behind the words.
Right. Like the difference between someone just reading words off a page versus actually telling you a story. One is flat and robotic. The other, like, has life and feeling behind it.
Yeah, that's a great way to put it. The researchers wanted to test whether scaling up Llasa would make it more like a storyteller, so they came up with all these clever tests, giving Llasa text prompts that would challenge its comprehension.
So, like, what kind of challenges? Give me an example.
Well, for English, they threw a whole bunch of different things at it: questions, emotional statements, really complex sentences, even tongue twisters. They wanted to see if Llasa could not only pronounce the words correctly, but also, adjust its intonation to sound natural, like when asking a question, for example.
So it wasn't just saying the words right, it was saying them with the right feeling, the right emphasis. Did they do anything similar for other languages?
Yeah, definitely. They did a lot of tests with Mandarin Chinese too. Those were even more complex. Think like Chinese poetry with rare characters and polyphonic words.
Polyphonic words. I don't know if I've heard that term before.
It means that the same word can have different meanings depending on the tone you use. It's a real challenge for language models to get those right.
Got it. So how did Lhasa handle all of that? Did it pass the tests?
The results were really impressive. The larger Llasa models did significantly better on those comprehension tests. It was like they could understand the text on a deeper level, which meant the speech they generated was more expressive, more natural, more human-sounding overall.
So they weren't just mimicking, they were starting to get the actual meaning behind the words. That's pretty amazing. Did the researchers find anything else as they were scaling up Lhasa?
Yeah, they actually did, and this is where it gets really exciting. They found that the scaled-up Llasa models started showing this really incredible capability. They call it zero-shot TTS.
Zero-shot TTS. Okay, now that sounds like something out of a comic book. What does that even mean?
It basically means that Llasa can generate speech for a brand new voice, one it's never heard before, without needing any specific training on that person's voice. It's like voice cloning on the fly. And it can even copy the speaker's style and emotional tone.
Hold on, did you say voice cloning? Like, if I gave Lhasa a recording of your voice, could it generate speech that sounds exactly like you, even saying things you've never actually said?
You got it. That's basically what it can do. They tested this using a few different datasets, including some that are specifically for evaluating TTS systems and others that focused on emotional speech. And they looked at metrics like how similar the generated voice was to the original speaker, how intelligible the speech was, and even how well it captured the original speaker's emotions.
So it's not just copying the sound of the voice, it's copying the emotions, too. That is wild. So what did they find? Did scaling up Lhasa help with this zero-shot TTS capability?
It did. The researchers consistently saw that the larger models, trained on more data, were better at both cloning voices and capturing emotions.
Okay, this is getting into some serious science fiction territory. An AI that can create realistic speech for anyone with any emotion. It's kind of incredible, but also, if I'm being honest, a little creepy. But I do have a question about all of this. We've been talking about scaling during the training process, right? But is there a way to make Llasa better once it's already been trained, like while it's actively generating speech?
That's a great question. It leads us to one of the most innovative parts of this research. The team experimented with what they called inference-time scaling, which is basically using more computing power during the speech generation process itself.
So instead of just making the model bigger or giving it more data up front, they're finding ways to make it like smarter in the moment as it's actually creating the speech. Interesting. How do they pull that off?
Well, they did this by introducing something called verifiers. Think of them as like AI critics that are listening to the speech as it's being generated and giving feedback from different angles.
So like a panel of judges at a singing competition, each judge is looking for something different, like tone or accuracy, and they give feedback to help the singer get better.
Precisely. Just like with judges, these verifiers have their own specialities. Some focus on making sure the generated voice matches the target speaker. Others analyze the emotions being conveyed. And others might focus on whether the speech accurately reflects what was in the input text.
It's like a whole team working together to make sure the final speech is as good as possible. So what kind of verifiers did they use? How do they actually work?
They mainly experimented with two types: output reward models, or ORMs, and process reward models, or PRMs.
ORMs and PRMs. Okay, break that down for me. They both sound like they're evaluating the speech, but maybe at different stages.
You got it. So ORMs are like those judges who give their scores after the performance is over. They look at the whole speech segment and give an overall score. It's a simpler approach, but doesn't allow for, adjustments during the performance itself.
And PRMs are more like the coaches, working with the singer during rehearsals, giving feedback along the way.
Exactly. They evaluate the speech generation step by step, giving much more detailed feedback. It's more hands-on and can give you more control, but it's also more complex and requires more computing power.
So it's a trade-off, simple versus fine-grained control. Did the researchers have any, challenges or make any interesting discoveries as they were playing around with these different verifiers and scaling strategies? So it's a trade-off, simple versus fine-grained control. Did the researchers have any challenges or make any interesting discoveries as they were playing around with these different verifiers and scaling strategies?
Oh, yeah, they did. It turns out that fine-tuning this whole speech generation process isn't as straightforward as you might think. For example, like if they focus too heavily on just one aspect, like making the speaker similarity absolutely perfect, well, sometimes that would actually make the generated speech harder to understand.
Really? So you could have a voice that sounds incredibly realistic, but you can't actually make out what they're saying.
Exactly. It's like imagine someone doing a really good impression of a famous person, but their impression is so over the top that you can't understand what they're actually saying.
Okay, yeah, I get it. So what happened when they tried to prioritize the understandability of the speech, like making sure the words were as clear as possible?
Well, sometimes that led to speech that was a little too perfect. You know what I mean? It kind of lost some of its naturalness, that unique character of the original speaker. It was almost like it became too robotic, trying to get every word perfectly clear.
Ah, so it's all about finding that balance, right? You want accuracy, but you also want naturalness, and you want to keep those individual characteristics that make each voice special. So how did the researchers tackle this?
So they came up with a really clever strategy. They called it partial PRM. Basically, it's like imagine a singer who's got a vocal coach helping them during warm-ups, but then when it's time for the actual performance, they're judged by a panel of experts. So the singer gets that personalized guidance early on, and then the judges focus on the overall quality of the performance.
Got it. So it's the best of both worlds, detailed feedback during the process, and then that final polish from the judges to make sure it all comes together. So did it actually work, this partial PRM thing?
It did. This hybrid approach, using both PRMs and ORMs, really helped. They saw big improvements in both speaker similarity and content accuracy, so they were able to create speech that was both realistic and clear.
That's really cool. So we've been talking about text-to-speech this whole time, but I have to ask, did the researchers explore any other applications for this Llasa framework? It seems like it could be used for other stuff too.
You're right, and they actually did. They tried adapting Llasa for something called automatic speech recognition, or ASR, like those systems that transcribe your voice into text.
Oh, interesting. So instead of generating speech from text, they tried using Llasa to go in the opposite direction, from speech to text.
Exactly. They kind of flipped the script. They kept that same Xcodec 2 tokenizer, but they changed how they were using it. Now Llasa was being asked to predict text based on audio input, not the other way around.
So did it work? Could Llasa, understand speech as well as it could generate it?
The results were really promising. They tested it on a standard benchmark data set for ASR, and Llasa actually did pretty well. It wasn't quite as good as the very best ASR systems out there, but it wasn't too far behind. It really shows how powerful this unified approach using LLMs for speech could be. Maybe we'll see it revolutionize not just TTS, but the whole field of speech technology.
That's amazing. So they've basically taken this one core technology and shown that it can work for both sides of the speech coin, both generation and understanding. That's a game changer. This whole field is just exploding right now. What are some of the big questions we should be thinking about as this technology continues to evolve?
There are so many exciting possibilities, but also some important things to consider, like will this unified approach become the new standard for speech tech? What new applications are we going to see as these models become even more sophisticated? And as these models get better at creating, realistic, emotionally nuanced speech, how do we make sure they're used responsibly?
That is a great point. There are definitely a lot of ethical considerations to keep in mind as this technology develops. Well, that wraps up our deep dive into the world of Llasa and what these large language models might mean for the future of speech technology. It's a field that's ripe for innovation, and research like this is paving the way for some really mind-blowing possibilities.
It's a really fascinating time to be following this field, that's for sure. And as always, remember to stay curious. There's a whole world of knowledge out there waiting to be explored.
We'll include links to the paper and other resources in the show notes, so be sure to check those out. And thanks for joining us. We'll get you next time on The Deep Dive.